All right, let's start off with a simple mind twister. This is kind of a commonsensical thing. You may know the answer. You got a car and SUV traveling at 60 miles per hour, right? They will lock up their brakes. So they will both skid to a stop. So they both of them are going to be skidding while coming to a stop. So the question is, which one will come to a stop sooner? Is it the car or is it the SUV or is it both at the same time? All right, so you kind of have an answer, right? What is your answer? This is a bit of a mild. Okay, so Ray says the car is going to come to a stop sooner. I think most of you guys are going to say the same thing. Okay, Connor, yeah, let's pretend that the brakes are equal. All right, let's pretend that it's the same. You lock up the brakes. As soon as you lock up the brakes, they will go into a skid. So they're going at 60 miles per hour. Everything being equal, which one will come to a stop sooner? Okay, so most will say the car will come to a stop sooner. Okay, who wants to make the argument that the SUV is going to come to a stop sooner? All right, not a single person is wanting to go in that route. Okay, that's perfectly fine. All right, so which one comes to a stop sooner?
It's been a week of bad weather and bad road conditions across much of the nation, a time when people with four-wheel drive vehicles feel like they're really in the driver's seat. Those top-selling SUVs and four-wheel drive trucks can go just about anywhere. But some drivers apparently think that means they can also do just about anything, and that's a mistake. Some experts say it could be a dangerous one. Here's Dawn Fratangelo with a Dateline Consumer Alert.
It's snowy. It's slippery. And maybe you're like Gil Oles, who bought one of those super-selling four-wheel drive sports utility vehicles, or SUVs, thinking it was safer and could handle the rough and wild weather better than a car.
In any icy condition, I take a four-wheel drive vehicle over a regular car because it just, you feel more in control.
Not so fast. Gil's pride and joy no longer looks like this after he hit a patch of ice.
I was not able to stop in time because of the icy conditions.
And look what happened to this man's SUV during last week's storm in the Midwest. Luckily, his injuries were only minor. And while accidents can happen for any reason in any vehicle, some wonder if SUV drivers know the limits of their vehicles in bad weather.
It appears that the urbanites get transformed into invincible people who go out and take risks and chances that in a regular car they would never even consider.
AAA automotive expert Dave Van Sickle says often it's not the vehicle. There's just something about SUVs that can change a city slicker into hell on wheels.
Perhaps it's this situation where you sit a little bit higher and you look down on everyone, and it breeds this sense of superiority.
Or maybe it's because owners buy into those television commercials. Trucks avoiding logs and boulders, nearly flying in the air and plowing easily through snow, perhaps giving drivers a false sense of security.
There is no question four-wheel drive vehicles offer better traction in the snow and can get through bad weather conditions when other cars cannot. But there is one thing they do not necessarily do better than any other vehicle. What is the biggest mistake that SUV drivers make in bad weather?
Underestimating the stopping distance.
Some motorists assume since they have four-wheel drive, their SUV will stop quicker.
Can an SUV stop better in bad conditions than, say, a Honda Accord?
Absolutely not. In fact, even on dry pavement, an SUV takes longer to stop than an ordinary car would.
Because of the weight of the vehicle, does it take longer for it to stop?
Oh, yes, absolutely. The heavier the vehicle, the longer it takes to stop.
And SUV drivers learned something else during Chicago's record snowfall. Enormous snowbanks so easily tackled in those TV commercials were impenetrable. Yet some drivers still push their SUVs to the limits. Transmissions fizzled, axles snapped.
If you get stuck in deep snow, you could burn out that four-wheel drive just trying to dig yourself out of it. You're not going anywhere. If you're stuck, you're stuck.
At Guy Manischello's collision repair shop, the 4x4s were coming in one by one.
It doesn't mean you're Rambo and Superman. You still have to exercise caution. A lot of times people haven't even read their owner's manual to know how the four-wheel drive system works.
There are no national statistics on the frequency of SUV crashes in poor weather, but in 1995, the Denver Post reviewed winter accident reports along the main interstate in Colorado. It found 43% of accidents involved four-wheel drive vehicles, even though they accounted for less than 25% of all vehicles sold in the state. We talked with some of the manufacturers of SUVs. Among their comments, severe weather is difficult for everybody. There is no evidence SUV drivers are more aggressive. The vehicles are among the safest on the road, and the ads don't influence people to drive irresponsibly. Still, when the bad weather hits, some car drivers would disagree.
There's absolutely nothing more frightening than to look in your rearview mirror and see 4,000 pounds of SUV coming down on you at a speed where you know they don't have a fair chance of stopping.
Safety experts remind us that four-wheel drivers should follow the same rules everybody else does. Don't speed, don't tailgate, and remember that four-wheel drive only helps you move better in bad conditions. It won't help you stop.
What happened?
Their SUVs snowbank so easily
Snow and can get through bad weather.
Underestimating the stopping distance.
Some motorists assume since they have four-wheel drive, their SUV will stop quicker.
Can an SUV stop better in bad conditions than, say, a Honda Accord?
Absolutely not. In fact, even on dry pavement, an SUV takes longer to stop than an ordinary car would.
Because of the weight of the vehicle, does it take longer for it to stop?
Oh, yes, absolutely. The heavier the vehicle, the longer it takes to stop.
All right, so that's what you guys said. Okay, so how about the following? Imagine that you have two cars, identical in every single respect. except one car has an anti-lock brake system, the other doesn't. The one without the anti-lock brake system will skid to a stop. The one with the anti-lock brake system will come to a stop without skidding from 60 miles per hour. All right, so which one, if any, will come to a stop sooner? The one with the anti-lock brake system or one without? What do you guys think? All right, so Sarah says, every single person who's saying something, give yourself 5 points. Okay, I'm reading your comments. I'm noticing that every single person says that the vehicle with the anti-lock brake system will come to a stop sooner. ABS system, anti-lock brake system. All right, that's just what you guys are saying. Okay, so give yourself 5 points for that one. The reason why I'm asking this question is because 50% of you guys don't know the right answer. Okay, so I know it's 50% because I've been doing this stuff for, I don't know, 20 plus years. And every single year when I ask this question, 50% of the students, the 50% of the people in general don't know what the correct answer is. I would have never thought that there was anything to discuss regarding this question because I always figured that everyone knew an answer. It's kind of like the earth, is it flat or is it round? Okay, guys, everybody knows the answer. If you think it is flat, you're just being disagreeable. That's it. I don't think anyone in the 21st century would doubt that the earth is round. Okay. If somebody says that, I'm thinking, okay, I'm not interested in this conversation. And this is one of those things. Which vehicle is going to come to a stop sooner? Is it the one with the anti-lock brake system or without? It's a simple question. Evidently not so. 15 years ago, I'm at a sports bar. All right, watching football and grading. If you're watching football, you know, the quarterback passes the ball, the wide receiver receives it, he gets tackled, you got a 30-minute break, 30-second break usually. All right, so it lends itself to grading and enjoying the game. So it's a nice distraction either way. Except there are two people sitting at the table right next to mine. And one guy was really proud. He loudly claimed that, hey, I got a new car. He's talking to his buddy. I got a new car. He said, it just cost me, it came with an anti-lock brake system, and anti-lock brake system cost me only a few $100 extra. And the guy said, wait, nuts? He said, you wasted your money. The other guy said, what do you mean? He said, you wasted your money. Yeah, you're going to be able to control that car better, but that car is not going to come to a stop any sooner. The other guy, seeming offended, he said, no, you don't get it, pal. He said, I'm going to be able to control the car better. That car is also going to come to a stop sooner. So these two disagreed back and forth, like 5, 6, 10 minutes. And then I started to get pissy because I want to focus on the game, and I can't focus on the game because these two are discussing physics. And at some point, I just started to feel really, really aggravated. I almost wanted to get up and say, hey, you two just shut up. Let me give you the answer. I know the answer because I'm a physicist, but you can't do that, guys. It's a bar, and the physicists don't belong in there. And then I was thinking to myself, I wonder what percentage of the people don't know. Evidently, it's 50%. It's been 50% forever. It's kind of weird. Anyway, so a couple of years later, I ran into one of our graduates from the art school. This guy was an exceptional 3D animation artist. This guy was gifted. I figured that he was going to, upon graduation, he was going to start working for Disney. And he was going to make a name for himself. Exceptional talent. Anyway, so when I ran into this guy, you could tell he was doing really well for himself. Number one, he was driving a real expensive car, sports car. It looked like at least $500,000. He was wearing a 3-piece suit. So I said, how's life? He said, great. I said, so how's the animation business treating you? Which was kind of obvious that it was treating him real well. He said, I have no idea. He said, I don't work in animation anymore. I said, really? What happened? He said, right after graduation, he got a job working for one of the animation studios, except he was going up against these really hard deadlines. So he was working like 80 plus hours a week, and he was making about $60,000 a year. He got burned out. Always liked selling cars. So he was actually selling expensive cars to rich people. He was working for one of those dealerships, and the car that he was driving that day wasn't his car. Obviously, he was on a lunch break, so he grabbed one of the cars. All right, so I said the anti-lock brake systems. I said, do they work as advertised? He said, Canon, no. He said, you'll be able to control the car better, obviously. He said, but that car is not going to come to a stop any sooner. In fact, he said that car is going to take a little bit longer to come to a stop. I said, if that's the case, why have the anti-lock brake system? He said, because he said they're pushing for the anti-lock brake system because it's an extra gadget and they were making more money on it. All right, he said, it's all money. It's all economics. That's what it is. Is she right? We'll find out. Remember the car versus a train. So imagine that both of them are going at 60. Both of them will lock up their brakes at the same time. So which one, if any, will come to a stop sooner? Okay. You know the answer for this one, right? Which one comes to a stop sooner? I think every single person knows the answer. So the answer is the car is going to come to a stop sooner. There's no question about it. So the question is why? And you guys will say the same thing because car is lighter, right? All right, car is lighter. It's going to require less.
And in case you think a speeding train could simply stop if you were on the tracks in front of it, consider this. A fully loaded freight going 60 miles an hour might take 1.5 miles to come to a halt after the brakes are applied. That's the length of 25 football fields. 60 miles an hour might take a loaded freight going, consider this. A fully loaded freight going 60 miles an hour
So it's going at 60.
might take a mile and a half
So you lock up the
to
brakes.
come to a halt
Mile and a half.
after the brakes are applied.
Do you think it's going to take a mile and a half for it to come to a stop? Does that sound right to you guys?
That's the length of 25 football fields.
Does anybody find that objectionable? All right, moving forward, we'll get back to those observations. All right, so let's talk about. No, I agree with that. Okay, let's talk about basically give yourself 5 points. External forces cause acceleration, right? So if something is accelerating, it's accelerating because of an external force acting on it. That's what it means. If something is accelerating, it's accelerating because there's an external force acting on it. If it's speeding up, external force. Slowing down because of an external force. Changing direction, there's an external force. That's what it means. All right, so every time we walk, you know, you can speed up, slow down, and change direction at will, right? At least it feels like it. So every time we walk, given the fact that we're able to speed up, slow down, and change direction at will, where does the external force come from that allows us to actually accelerate? You're thinking it comes from your muscles. I'm thinking, no, you can't make that statement because the muscles will generate an internal force. Remember, you cannot lift yourself up by grabbing your nose in the opposite direction or the other arm. It's simply not going to happen. All right. For you to be able to lift yourself up, you have to use external means for something like that to happen. So whenever we're walking, obviously there has to be an external force that's causing us to accelerate, speed up, slow down, or change direction. So where does the external force come from? If you're thinking that's the invisible hand of destiny, think again, guys. So where does the external force come from that allows us to accelerate? All right, you know it's going to come from the ground, right? So what happens is you apply a force on the ground in the backward direction, in the opposite direction of your motion. So the action force is going to act on the ground. In turn, the ground is going to apply the same force back on you in the forward direction, in the direction of motion. So the action force is going to be applied to the ground. The reaction force is going to be applied to you. So the reaction force is going to be applied back on you, in essence. So that's what happens. Now, you apply a force on the ground through friction. You apply a force on the ground through friction in the backward direction, and the ground through friction applies the same force back on you in the forward direction. So what makes this possible is the frictional force. Surface friction, the frictional force. Now, none of us would be here today if it weren't for friction, guys. None of us. And you know what I'm talking about, right? I'm talking about walking or driving. You can't get around without friction. You can only go through the motions. All right. Without friction, you cannot move. You cannot move at all. You would just stand still here, just going through the motions. All right. So only through friction, you're able to apply a force on the ground. And ground is going to be able to apply the same force back on you as a reaction force in the direction that you want to move. So the question is,
of how it works. Look at this video from ITT Automotive, a company that manufactures ABS systems. First, watch what can happen without ABS. Then, with ABS, the driver stops in time and maintains control of the car.
all right, so
Of how it works.
it's the same car,
Watch what can happen
the same driver.
without
So what do we know?
ABS.
As it so happens, it is true that you control the car better when you have the ABS, anti-lock brake system.
The driver stops.
But also it's true that the car comes to a stop much sooner. All right. With
Of
the
how
anti-lock
it
brake
works.
system,
Then, with ABS,
you control the car better.
the driver
It'll come to a stop much sooner.
stops in time without ABS.
Without the anti-lock brake system, it's going to be tough to control the car. Also, it takes longer for it to come to a stop. Both scenarios, the cars are moving at the same speed.
Company that
They got the same initial speed.
manufactures ABS systems. First, watch what can happen without ABS.
Without the anti-lock brake system, control is difficult. Also, it takes longer for it to come to a stop. So those of you guys who thought that the cars with the anti-lock brake systems will come to a stop sooner, absolutely correct. Give yourself 10 points for that one. Here's the question though, guys. In either scenario, whether the car is skidding or whether or not there's an anti-lock brake system, what's stopping the car is the frictional force, right? So the question is, when you have the anti-lock brake system, the car obviously experiences more friction. So how is that possible? How does the anti-lock brake system generate more friction on the car? All right, so which means that we have to focus on the contributing factors to friction.
Cool, yeah.
Here's a question for you. Does the size matter when it comes to friction?
I know those first ice boats had a lot of speed, but not a whole lot of control. Yeah, with the blade sitting there, he couldn't steer around the ice fishing holes. Oh, geez, learned the hard way. Wiser is better.
With its speed-sensitive steering technology, the White Track Land 3 gives you precise cornering and control, even at a good clip.
You betcha. Better.
Wider is better. The White Track Land 3 by Pontiac.
All right, so does the size matter when it comes to friction? Yes or no? Okay, so most of you guys will say yes, right? I mean, that's common sense. Everybody's going to say yes. Bigger the surface area of contact is, the more the friction is. Okay, so let's take a look at the contributing factors from a commonsensical perspective. All right, so we're looking at surface friction, lowercase f. It's going to be proportional to the surface area of contact. It's common sense. Okay, so A represents the surface area of contact, A area of contact. All right, second contributing factor that we can come up with. How about the nature of surface, guys? How about the nature of surface? All right, so which gives you more friction, for example? Is it carpet or is it ice? All right, so the second one is frictional force is going to be proportional to the nature of surface. Okay, for whatever the reason, I don't know what the main reason is, but we get to use the Greek letter mu for the nature of surface. Nature of surface gives you a traction number. The technical term of it is the coefficient of friction. Coefficient, it just means a number. All right, so it's a friction number or it's a traction number. So it's a number of friction, coefficient of friction. It's an experimental number, which means that this value is going to be measured. All right, so this mu that you're looking at is known as the coefficient of friction. It's an experimental number. So which means that the coefficient of friction from ice is going to be smaller than carpet. So which means that carpet offers a lot more friction or traction in essence. So the third contributing factor that we could come up with, commonsensically, it's the weight, right? I mean, heavier objects will experience more traction. So the heavier objects will experience more traction. Okay, so I want you to see this. So I'm just gonna stop this, go to the video. All right, here's a piece of paper. Okay, so we will play with this. Okay, the sound that you're hearing is caused by friction. Okay, when I press on it, notice that the amplitude of the sound goes up. It's louder. Okay, so this versus this versus this. When I press on it, I'm increasing the frictional force. In fact, I press on it further, it hardly moves. So by increasing the weight, I'm able to increase the friction, right? By pressing on it, am I increasing its weight? Yes or no? You may think so, but in reality, it still weighs the same, guys. I'm not changing its weight. What I'm changing is by pressing on it, I'm changing the apparent weight, the normal force. Reaction force is going up. Reaction force is sensitive to, it's going to be sensitive to the downward force. All right, so by pressing on it, what I'm doing is I'm increasing the normal force. I'm changing its apparent weight. All right, so the frictional force is going to be sensitive to the apparent weight. All right, so larger the apparent weight is, the larger the frictional force is going to be in this case. So we got three contributing factors. It's going to depend on the size of the surface area of contact. It's going to depend on the coefficient of friction, that's the nature of surface, the traction number. It's also going to depend on the weight or the apparent weight of the object. Okay, so your common sense is going to say all of them are good. I'm happy. These are the contributing factors. Except I got news for you. Out of the three, one of them is not going to contribute to friction at all. So the question is which one? So if you had to pick one to get rid of, which one are you willing to jettison? Which one are you willing to abandon? Which assumption? All right, so put down your thoughts on the side. I just want to get a quick idea of which one you guys go. If you had to abandon one of them, which one would you say is not relevant? All right, so Juan said the second one, nature of surface doesn't matter. Ray said that the apparent weight is not going to matter. Okay, so, or surface area. So all of you guys end up picking something different, which is fine. Okay, so, all right, so give yourselves 5 points for actually every single person who says something. All right, so if you're right, you will add 10 points to it. All right, so every single person made an assumption. It's based on some kind of a gut check at this point, okay? Because what else do you have going for you? Every one of them made sense to you. Now you have to abandon one of them. So the question is, which one do you want to abandon? All right, so let's check to see what our options are. Nature of surface does matter, guys. This is the one we will get to keep. You're not going to get the same amount of friction from carpet that you're getting from ice. Okay, I said it wrong. You're not going to be able to get the same amount of friction that you're getting from ice that you're getting from carpet. Either way, it makes sense. So nature of surface does matter. Not only the nature of surface is going to
are closed now for cleanup, and they're going to remain closed until the Thursday morning rush hour. But it is ice that is the problem in Little Rock, Arkansas. Dangerous driving there. The ice storm is also causing problems.
Also, the conditions of the surface will matter, right? It's the road when it's dry, plenty of friction. When it's wet, the friction goes down because the traction goes down. When it's icy, forget
problems
it.
At airports.
All right, so the friction between materials, coefficient of friction that you're looking at, mu, is located here. Rubber and concrete is what we're focusing on. For a dry surface, it's going to be 1.2, so that's the amount of traction that you get from the surface. As soon as the surface is wet, traction goes down. That's what it means.
2 people, 2 accounts.
Also, another thing that I want you to know is that the different surfaces is going to give you different amounts of traction. Glass on glass is different. Aluminum on aluminum is going to be different. All right, steel on steel is going to be different.
2 people, 2 accounts, 2 conclusions. In the science of crash investigation, the unpredictable element is the human factor. 2 people, 2 account crash investigation.
All right, so 2 of the tires are on asphalt, 2 on grass. If you break it,
unpredictable.
There's going to be a tremendous amount of friction from asphalt, not enough from grass. You're going to have a really hard time controlling this car. Hence the cause for this accident. Weight does matter. I did a small demonstration. When I press on it, when I changed its apparent weight, the frictional force got much larger. All right, so I was able to magnify the frictional force by pressing on it. So the weight, the apparent weight, is going to matter. One thing that doesn't matter is the surface area of contact. When they say the size doesn't matter, This is what they mean. Size does not matter when it comes to friction. When it comes to friction, the size does not matter. When we say size, we mean the size of the surface area of contact doesn't matter. All right, so the size of the surface area of contact does not matter. Now remember, the frictional force is going to depend on the coefficient of friction, so the nature of surface. It's going to depend on the apparent weight. So what happens when you increase the surface area of contact? What happens, that weight is going to get dispersed onto a larger surface area. So the pressure goes down. So it's not going to change the frictional force. It gets dispersed onto a larger surface area without changing the frictional force. All right. So, but the funny thing is, your mind is not going to comprehend this immediately. All right. Your mind is not going to agree with it immediately. Case in point, your common sense is going to be loud. And then you're not going to be able to let go of the fact that the size doesn't matter. Now, if the size doesn't matter, okay, let's have a quick discussion. Why do the race cars have wider tires? Why would they have wider tires if the size doesn't matter? All right, how do you explain that? All right, so what's happening in your heads right now? If the size doesn't matter in terms of generating friction, the traction or whatever, why would the race cars have wider tires? What would be the purpose of it if not to generate more friction? What do you guys think? All right, so I'm looking at some of the answers. Race test stability, I'll give you 5 points. Briar says weight, I'll give you 5 points. I don't, oh, do you think it's going to increase the weight, that increases the friction? That's not a bad way of looking at it. That's, damn, never even considered that, because they want to keep these cars as light as possible. So I'm not sure if you want to actually increase the weight. Juan says more control. So Juan, you're making a good point, but how does having wider tires allow you to actually control the car better? What's the idea behind it? Okay, do you know what you're thinking? You're thinking that you control the car better because it's going to generate more friction. That's what most people say. In reality, it's not going to generate more friction. All right. Okay. So now that we've debated it a little bit, we didn't really debate it. Now that I made it murkier, let's go back and come up with a reasonable explanation. Okay. Now think of it this way, guys. Let's go to the other extreme. If the size doesn't matter, the size of the surface area of contact doesn't matter in terms of generating friction, why not have bicycle tires on our cars? All right, just come up with some, I don't know, indestructible rims. Yeah, it's not going to look as cute. I get it. Why not have bicycle tires on the cars? Okay, about 100 years ago, literally, when they started building cars, all right, the width of those tires were slightly wider than modern cars, slightly wider than the bicycles. All right, so they had, the tire widths were slightly larger than the bicycle tires. So what is it that they discovered when they had tires with that amount of width? Is what they discovered. The weight of the vehicle on the tires need to get distributed onto a larger surface area, number one, in order to reduce the pressure on the tires. So you like to make the tires as wide as possible because of it. And number two, there's a drive force, the thrust generated by the engine acting on the tires. Once again, that drive force needs to get distributed onto a larger surface area in order to reduce the pressure on the tires. So you want to reduce the pressure on the tires as much as possible so that the tires don't wear and tear and blow out. 100 years ago, those tires did not last more than a month. Of course, we got better chemistry today, and so the tires are much better, but that's besides the point. Also, the cars are much faster today. Race cars, those things go over 200 miles per hour. 200 miles per hour. Tremendous amount of force, drive force acting on those tires. So what do you have to do? You got to disperse it onto a much, much larger surface area in order to reduce the pressure on those tires so they don't wear, tear, and blow out easily. And they still have to keep changing those tires. I don't know after how many laps, 100 laps, 50 laps, I'm not sure, but they have to. All right, so Sarah, give yourself 5 points. It's the tire pressure. It's the tire pressure. That's the main reason why. So they're trying to actually reduce the tire pressure as much as possible so those tires can last longer. Okay, good. I'm seeing a lot of C's, and you guys didn't get fooled by D. Okay, so you guys, this is actually pretty damn good, because most people would still pick D over C. All right, so obviously you guys connected with the idea that the surface area does not matter. All right, so give yourself 5 points for that one. So that's, I'm actually delighted by that one. Okay, so what are we doing? Out of the 3 contributing factors, we're going to get us in the first one. Okay, so that's not a contributing factor. So a coefficient of friction is going to matter, and the apparent weight is going to matter. So those are the only 2 contributing factors. Now we came up with a summary statement for the surface friction, which happens to be that formula. All right, so the next thing we need to analyze is
what can happen without ABS.
Without ABS.
Then
versus with ABS. So when you have the anti-lock brake system, magically the vehicle is generating more friction, right?
The driver's.
So the question is how? What's going on? How's that possible? All right, so let's study. Let's take all the time you need. I'll give you guys one more second. Okay, time's up. What's wrong with this picture? Artistically, not the best. It's not done by one of my students. And from physics perspective, this is horrible. This is atrocious. What's wrong with this picture? What's wrong with it is the way she's pushing up against the cabinet. What do you think is going to happen to the cabinet, the file cabinet, if somebody were to push it this way? It's going to topple, right?
No. I gotta go.
Dom, could you call me an ambulance? Hey, hang on. I was waiting for that. Need another phone line?
It's going to topple. All right, ignore that. All right, so obviously she's trying to move the file cabinet. Here's the applied force, so that's the force that she's applying. Friction is countering that motion. All right, so opposing that motion. This is the frictional force. All right, so take a look at the forward force, the applied force, and take a look at the size of the frictional force. All right, notice that the size of this arrow matches the size of that arrow. So what's the net force acting on it? All right, so you got two forces, equal magnitude, opposite direction. So they will add up to 0, right? So the net force acting on it is 0. This is what it is. So which means that this file cabinet is not going to move. It's not moving. It's not going to move. Frictional force is just canceling out this push in essence. All right, so if that's the best that she could do, this file cabinet is not going to go anywhere, so she's going to get help. No, both of them are pushing, right? Both of them are pushing. All right, so the force increased, and so is the frictional force. They're still equal to each other. So the net force is still 0, and it's not moving. One thing that happened, though, notice that when there's an applied force, and then when the frictional force balances it, this thing is not moving. There's friction. Friction is the reason why it's not moving. This sort of friction is called static friction. Static friction means that the surfaces are at rest with respect to each other. All right, so she pushes in this direction. It generates a frictional force opposing the motion. The force of friction is the static friction. Now, both of them are pushing. There's still static frictional force. But what happens is this static frictional force is maximized. So what happens when the frictional force is maximized? When the static frictional force is maximized, at that point, it's going to start to slide. It's going to start to skid. All right, when you maximize the static frictional force, at that point, it's going to start to slide. It's an automatic thing. It's the maximum. It's going to hit the maximum. And as soon as it starts to slide, something weird happens. Okay, now, I want you to take a look at the size of this force, and I want you to take a look at the size of this force. Size of this force is the same as the size of that force. Okay, so the applied force doesn't change. Okay, applied force doesn't change. But what happens is, when the static frictional force is maximized, look what happens to the size of the frictional force. It's going to go from static to sliding friction, which is known as kinetic friction. So it goes from static friction to sliding friction. So what happens? Look at the size of the static frictional force when it's maximized, and look at the size of the kinetic friction while it's sliding. Notice that this became smaller. So the static frictional force, the maximum static frictional force is going to be larger than the sliding friction. All right, so the kinetic frictional force here is going to be smaller than the maximum static frictional force. Forward force is still the same size as before. Backward force in this case is going to be smaller. So there's going to be a net force acting on it. So this thing is going to accelerate. Okay, let me go back and repeat the point that I'm trying to make a couple of more times. Sliding friction is going to be smaller than the maximum static frictional force. What that means is it's going to take a lot more force to make something move than keeping it moving. That's what it means. That's called a life experience. It's going to take a lot more force to get something to move than keeping it moving. All right, so you have to reach this threshold. As soon as you maximize this static frictional force, it's going to go into a skid, which means that static friction will become kinetic friction. So maximum static frictional force is going to be larger than the sliding friction. All right, so the next question is why? All right, so let's focus on rubber on concrete. Take a look at the traction number, the coefficient of friction. When it's static, as soon as the car goes into a skid, what happens? It goes down. It becomes 0.85. So in the case of static friction, coefficient of friction, the traction number is going to be 1.2. And as soon as the car goes into a skid, the traction number goes down to 0.85. That's what happens. It goes down. All right. Okay, very good. You guys got that? We got it. All right, so D is the best answer. Yours has 5 points for that one. All right, so let's continue with the discussion. So surface friction, there are two kinds. All right, Sarah, you made this point before, so give yourself 10 points for this one. You got static versus kinetic. Static means the surfaces are at rest. Kinetic means that one surface is sliding over the other one. Formulas look the same, except the coefficients of frictions will be different. All right, so this is the traction number for the static case. This is the traction number for the kinetic case. All right, so we know that the static friction, the maximum static frictional force, will be larger than the kinetic frictional force. The reason is because the amount of traction that you get from a static case is going to be larger than a sliding case. All right, the tires on asphalt, obviously, coefficient of friction for static friction is 1.2. Sliding friction, kinetic friction is going to 0.85. All right, because there's more traction in the static case, static frictional force near its maximum value is going to be larger than the kinetic frictional force. Okay, now conceptually it gets kind of weird. All right, this tire is sliding or skidding. So here's the coefficient of friction. And this tire is rotating, it's rolling. Okay, now here you end up getting sliding friction because the point of contact is sliding, right? So that makes sense. So how is it that you end up getting static friction when the tire is rolling though, or rotating? Any ideas? All right, so this one is a rolling or rotating tire. How does a rolling or rotating tire experience static friction? All right, so I'm just gonna look at the chat in case you guys are saying something. All right, I'm not. All right, you're not saying anything. All right, so let's move forward with this one. All right, so here's the answer, guys. You have to look at the point of contact regarding the tires. If the point of contact is sliding, kinetic friction. If the point of contact is stationary, static friction. Yeah, this tire is rotating, it's rolling, but wherever the point of contact is, the point of contact is always static with respect to the surface. So what that means is it's always going to give you static friction. So rolling tires will always give you static friction. Remember. All right, race, give yourself 5 points. All right, so the rolling tires will always give you static
Here's how ABS works. If you need to brake suddenly, an onboard computer pumps the brakes on each wheel at up to 18 times a second, faster than you ever could yourself. That stops the wheels from locking up, allowing you to safely steer around a hazard. All you have to do is apply steady pressure to the brake.
All right.
Here's how 18 times
per second. 18 times per second.
The wheels from
Intel brake systems will lock out the brakes 18 times per second. 18 times per second. Why?
Locking up.
What's the idea? The short answer is because Intel brake systems designed to maximize the average static frictional force. What does that even mean? Let me explain. All right, guys, when you put the brakes on, initially it's going to be all static until the static frictional force is maximized. This is your static friction. So what happens when the static frictional force is maximized? Boom, it goes into skid. It's going to start to slide. All right, notice that your kinetic frictional force is going to be smaller than only this region of the static frictional force. Only this region of the static frictional force is going to be larger than your kinetic frictional force. So what does the Intel brake system do? All right, so it's going to lock up the brakes and release the brakes, lock up the brakes, release the brakes. It does it 18 times per second. As a result, the average static frictional force is going to be larger than your kinetic friction. Okay, so let's say it again. This time I'm going to give you the same presentation, slightly differently. All right, lock up the brakes initially without the Intel brake system. So what happens is your static frictional force is going to become maximized if you don't have an Intel brake system. The car is going to go into a skid. So skidding friction, sliding friction is going to be smaller than this region of the static frictional force. So what does the Intel brake system do? It locks up the brakes, releases the brakes, locks up the brakes, releases the brakes within that period, 18 times per second. More often you do that, the larger the average static frictional force is going to be. As a result, this thing is going to come to a stop sooner. All right, so that's how that happens.